This is Pascal's line, which is the first projective geometry construction setup that I'm going to show you. So you're going to begin with a circle, and it doesn't actually even have to be a circle. It could be, there's other constructions that'll work as well, including two parallel lines or an ellipse, but we're going to go with a circle. And you're going to select 6 points on the circle, and these points don't need to be evenly spaced. They could be, and you'll actually get a result that's consistent, but if they're not evenly spaced, you'll see the result more clearly, and it also points to a greater generality if it's more randomly spaced, which is what these are. All right, so you have 6 points there that I've picked, and then what we're going to do is we're going to connect them consecutively, but when we connect them, we're going to extend the line outside of the bounds, because remember, a line actually goes on forever. It doesn't just end at the 2 points it connects, by definition. So that's the first line. There's the second one. There's the third one. There's the fourth one. There's the fifth one. And there's the sixth one. And this is actually a hexagon. Not a symmetric, evenly spaced hexagon, but a hexagon nonetheless. And we're also extending the lines, so it's greater than the hexagon that you would normally see that is just limited by the vertices. Here the lines extend beyond them. Next thing we're going to do is number them. And here we're going to number them consecutively. It doesn't really matter which one you start with, so long as the next one next to it is the second one, then the one after that is the third one, etc. So I happen to pick this line to be line 1, this line here to be line 2, and then line 3 is this one, line 4 is that one, line 5 is this one, line 6 is this one. This is often the most difficult part for many of my students, even though it seems straightforward to number consecutive lines. Sometimes it's easy to think that the one that you think is 3 is actually 4, or vice versa. I've had that happen many, many times. And then this construction won't work. But if you do everything correctly, and you label everything appropriately, and make sure that all your lines go straight through the center of the point, then this works out all the time. Next thing we're going to do, and I colored the lines to indicate the pairings, we're going to pair lines 1 and 4, which I drew in blue right here, 1 and 4, lines 2 and 5, which I drew in red, and lines 3 and 6, which I drew in green. The point at which those lines intersect, I'm denoting with another circle there. And you might notice something here about the 3 points where all of these lines intersect. And if you're observant, you'll notice that those appear to also be a line themselves, and they are. That is something called Pascal's line. You will always have a Pascal's line created in the way we talked about here. So you'll always, it doesn't matter which 6 points you pick. You can pick any 6 points on the circle. Follow the same procedure, you will end up with a Pascal's line. And that is a big deal. It was discovered, this phenomenon, or this construction, if you'd like, was discovered by Blaise Pascal in around 1789, if I'm not mistaken. And it is a fundamental and useful aspect to consider in projective geometry. Now you might also argue, wait a second, what if a couple of these lines were parallel? And I will show you that, because you might say, well, then they won't connect, and you won't get a Pascal's line. And that's not true. You still will. I'm going to show you that. I'm going to show you on a different one that I created. Here's a case where I went through that and came up with a case where we actually had parallel lines. So in other words, lines, this is line 1 right here, and this one here is line 4. They're parallel, so they never meet. But where they meet is actually way down here at the point at infinity, or if you like, way up here at the point at infinity. They will meet there at a point. And that's consistent here. If you look at lines 3 and 6, they cross at this point. Lines 2 and 5 cross at this point. Connect those 2 points with the red line. That is Pascal's line. And Pascal's line does connect to the point of intersection of lines 1 and 4 at the point at infinity. So Pascal's line is still valid here. It still works because all of these 3 lines will intersect at the point at infinity, just like this one here, that one there, but at infinity. Pascal's line.